December 15th, 1967. The Silver Bridge over the Ohio River is packed with rush hour traffic, Christmas shoppers, and heavy vehicles moving between Point Pleasant, West Virginia, and Gallipolis, Ohio. Inside one steel joint, a flaw no one can see is growing in silence. In less than 20 seconds, the bridge will fold into the river. What broke first, and why did one hidden defect bring down the entire span? The Silver Bridge opened in 1928, when the Model T era was fading and American road traffic was still much lighter than it would become decades later. It was an I-bar suspension bridge, a design that used linked steel bars and pins instead of the cable systems more familiar today. For years, it was a proud crossing on the Ohio River and a vital route for local commerce. The bridge was 1,860 feet long, with a 700-foot main span, and it connected Point Pleasant, West Virginia, with Gallipolis, Ohio. Built by the J.E. Greiner Company and constructed by Gallia County Ohio River Bridge Company and U.S. Steel's American Bridge Company, it was completed in just 1 year and opened on Memorial Day 1928. At the time, it looked modern, efficient, and strong, but the bridge had one dangerous trait. It was not built with the redundancy that later bridge engineers would demand. So if one major part failed, the load could shift too far for the rest to survive. That detail would matter far more than anyone understood in 1928. The Silver Bridge carried thousands of vehicles a day by the 1960s, including trucks far heavier than the bridge's original designers had imagined. So the question was never whether the bridge was busy. The question was whether the structure could keep absorbing years of stress without one invisible weakness becoming decisive. And that weakness had already been there for decades. The first problem was the bridge's design itself. The Silver Bridge used I-bars, long steel members joined by pins, and its structure depended on each piece doing exactly what it was supposed to do. There was very little room for failure. If one link failed, there was no real backup path for the load. At this point, the disaster was still avoidable. But the bridge had been built in an era when engineers did not yet understand everything about long-term corrosion fatigue and stress corrosion cracking. Then came the traffic load. By the 1960s, the bridge was carrying cars that were far heavier than the vehicles of the late 1920s. Trucks had also become a regular part of the crossing. The bridge had been designed for a different century, but it was living in the present. Therefore, every crossing added another cycle of strain to metal that had already spent nearly 40 years in service. Inspection records later showed that the bridge had been examined over the years, including inspections in 1959, 1963, 1964, and again after repairs in 1965. But the fatal flaw was not easy to detect. It was hidden inside a critical I-bar joint in a place that ordinary visual inspection could not reach. That made the danger especially cruel. The bridge could look serviceable, while a failure mechanism was developing inside it. What investigators would later find was even more troubling. The bridge had not been weakened by a single dramatic event, but by a slow combination of corrosion, stress, and a minute crack that grew over time. That crack was not something a casual observer could have spotted from the roadway. It was buried where no routine inspection could have seen it. One more piece made the bridge especially vulnerable. The structure had no tolerance for a single broken chain link. So once the first critical member let go, the rest of the bridge had almost no chance. At that point, the disaster was still avoidable in theory. In practice, the hidden flaw had already loaded the dice. And there was another layer of irony. The bridge stood over a major river, but the failure did not begin in the water, in the roadway, or in the towers. It began inside one steel eye in a place smaller than a hand. One tiny defect. One enormous consequence. Imagine driving across that bridge on a cold December afternoon, with traffic moving slowly and holiday errands on your mind. Nothing in the scene would have warned you that the structure was already close to collapse. That is what makes the Silver Bridge so disturbing. At about 5 a.m. on December 15, 1967, the bridge was crowded with rush hour traffic. Witnesses later described a loud, gunshot-like sound. Then the north side of the suspended span failed. The collapse happened fast, very fast. In less than 20 seconds, the entire suspended portion of the Silver Bridge folded and dropped into the Ohio River. Cars fell with it. Trucks fell with it. People who had been crossing to work, to shop, or to get home disappeared into the river in wreckage. The scene on the riverbank turned into immediate chaos. Witnesses saw the span sag, twist, and vanish. The bridge had not simply broken in one clean line. It had failed in a chain reaction, with the loss of one key member triggering the loss of the whole suspended structure. Therefore, once the first collapse began, there was no stopping it. 46 people died. 2 bodies were never recovered. 9 others were injured. 32 vehicles went down with the bridge. For the families waiting on either side of the river, the first news was not a report or a siren. It was the absence of cars that should have arrived home. The disaster also trapped the region in a transportation crisis. The Ohio River crossing was gone, and the local network had to improvise quickly with ferries, nearby bridges, and detours. But for those trapped in the moment, the bridge itself was the only thing that mattered. It had been there 1 second, and gone the next. What exactly failed inside the bridge was still unknown, but the wreckage already contained the answer. Investigators moved quickly after the collapse. The bridge was examined by state and federal authorities, and the National Transportation Safety Board later issued the formal finding. The key discovery was not a dramatic explosion point or a hidden bomb of metal fatigue in the abstract. It was a fracture in the lower limb of an I-bar eye at a critical joint in the north chain on the Ohio side of the span. That fracture had begun as a small flaw that grew over time. The final report concluded that the failure involved stress corrosion and corrosion fatigue, which developed into a critical size defect over the bridge's life. Once that member failed, the bridge's non-redundant design made total collapse inevitable. This is the moment the story changes. The missing washer idea is a myth. The real failure was not a loose part or a simple maintenance oversight. It was a microscopic crack in a critical steel member, hidden where ordinary inspection could not realistically find it without disassembling the joint. That detail mattered because it changed how engineers thought about bridge safety. The problem was not just that the bridge was old. It was that a hidden defect in one highly stressed component could destroy the entire structure when there was no backup path for the load. The official investigation also made clear that the materials and design practices of the late 1920s did not fully account for the long-term behavior of these components under real-world exposure. In other words, the bridge was not judged by the knowledge of 1928 alone. It was judged by what 40 years of service had revealed, and that revelation was devastating. A bridge trusted by thousands had been living with a flaw that no routine glance could expose. The single piece of evidence that explained everything was the fractured I-bar itself. Once that was understood, the collapse was no longer a mystery. It was a warning. The Silver Bridge collapse changed bridge safety in the United States. It helped push the country toward more rigorous bridge inspection practices and broader attention to structural redundancy. Federal action followed, including a national focus on bridge safety and inspection standards. A replacement bridge was eventually built, the Silver Memorial Bridge, which opened in 1969 near the site of the collapse. It stands as both a crossing and a memorial, reminding drivers that infrastructure failures are often not sudden mysteries, but the final moment in a long chain of missed vulnerability. Every time you cross a modern bridge, you are benefiting from lessons written in steel and grief. Engineers now pay far more attention to redundancy, fatigue, corrosion, inspection access, and the behavior of critical connections over time. That is why a single flaw is less likely today to bring down an entire crossing. But the lesson is larger than one bridge. It is about trust in systems that look permanent until they are not. A structure can carry traffic for decades and still hide a fatal weakness inside one joint, one pin, one eye. That is the haunting truth of the Silver Bridge. The collapse was not caused by a huge visible failure. It was caused by something small enough to hide, long enough to grow, and strong enough to kill.